if the test instrument has 98% specificity. That means ability to say negative to a negative condition. And 90% sensitivity. That means ability to say positive to positive condition. Okay. If we take a sample test and test result is positive, what is probability that sample has condition? I repeat the problem. In a clinical test for a blood cancer, a population of 10,000 was tested. 1% of the population has positive condition if the test instrument has 98% specificity, that is ability to say no to no. Okay, ability to say negative to a negative condition, and 90% sensitivity, that is ability to say positive to a positive condition. Then question is, if we take a sample and test result is positive, what is the probability that the sample has condition? Okay, so this is a real life example where we have to solve such kind of problems. Now let us try to solve this. Now given thing is specificity. Specificity is 98%. So that means it is a probability that test is negative when the true condition is negative. So what is specificity means? It is test instrument is giving you negative condition that there is no say cancer, or in today's scenario you can even take the case of corona. So test is negative, it is given by instrument, and true condition is also that it is negative. So that is called as specificity of the instrument. Then you have another specification called as sensitivity. What is sensitivity? It is, I think, 90% in our problem. So it is meaning is it is the probability of test is positive, that your instrument is saying that the person has cancer, provided that the person has really cancer. Okay, so this is known to us that this person is having cancer or this person is having corona, and the probability that the instrument will also say same thing is given here. For positive case, that given condition is positive, instrument is detecting it as positive is 90%. So you can say that there is a 10% chance that even you have a disease, this instrument will not detect it. Okay, and there is a 2% chance here that even though you have a negative condition, but still this machine will say, okay, you have a condition. Okay, say there is no corona, but still this machine will say there is corona. So you can see the complications of this kind of instruments socially when somebody is do not having this cancer and it is being said that you have cancer. Okay, so this is a quite bad condition socially. And when you have this second condition that you have actually say cancer but your machine is saying uh, uh, you don't have cancer, that is 10% chance is there, so that is more dangerous to the life. So your instruments are very sensitive and they must have very good specificity and sensitivity so that you don't face any problem. Now in this problem what is given to you is that the instrument is saying that you have a positive condition. What is chance that the person is really having that condition? So what is asked to you is probability that condition is positive when test is positive. Okay, so your machine is saying, so what is meaning of this is your machine is saying you have cancer, and what is really chance that you have cancer. Okay, so the reverse of this is asked, the reverse of this probability is asked to you. So what is best thing you can do is you can use again your Bayes rule. Now what is asked to us, I am writing here probability of condition is equal to positive given that test is positive. Okay, so this is equal to probability of test is equal to positive given that condition is positive multiplied by the prior, that is condition is positive, now divided by probability of test is equal to positive. Okay, so this I think we know everything about this problem now. So probability that test is positive when condition is positive, this is sensitivity, and which is 90%, that is 0.9, multiplied by what is chance that in a population of 10,000 how many people are positive. So with some good instrument it has been observed that you have only 1% of the population is having the condition. Okay, so this is prior knowledge, and divided by test is positive. So test can be positive in two conditions: you have condition or you don't have condition. So in both cases you may have your test positive. So I am writing both things. So we are using sum rule to calculate the denominator. Okay, now how to do that? So this is equal to, so denominator is equal to probability of test is equal to positive given that condition is equal to positive multiplied by probability of condition equal to positive. Okay, so plus, so since I'm using some rule, I will be writing here plus. So probability of test is equal to positive. Again, test is positive given that condition is negative into probability of condition being negative. Okay, so this is this application of your sum rule. So this will be 0.9 multiplied by 0.01. So as it is, now we have to write the denominator. So first thing, this one is 0.9 multiplied by 0.01. Okay, so this is 0.01 plus, now what is probability of test positive and given condition is negative. Can you find out? So this you can find out from the specificity. So specificity is given to us as probability that test is negative when condition is negative. So this is equal to point, I think 98. So I want probability of test is equal to positive and condition is negative. So how much this will be? This will be 1 minus 0.98. Okay. The sum of these two must be 1.0. You got my point? Condition is negative in both the cases. Thing is that I'm finding out probability for negative here and probability for positive here, so that the sum is always 1, and the first one is given to me in the problem itself. It is 0.98. So I can write here 1 minus 0.98 multiplied by what is probability of negative condition. Since only 1% of the population is having this problem, so I write here 1 minus, actually I should write 1 minus 0.99. Sorry, 1 minus 0.01. So this I can write as 0.9 into 0.01 divided by 0.9 into 0.01 plus 0.02 into 0.99. Okay, so if you solve this, this will come 0.3125. So what we have calculated is, it is the probability that condition is positive when test is positive. So how much is chance of getting the true result is 31.25% only. You got my point? If the instrument is saying that you have cancer, then there is a chance only 31.25% that you really have the cancer. Okay, it's very poor instrument that way. So similarly, you may have heard the instrument which, or the test which we carry out for rapid test we call for corona is around, I think, 50 to 60%. Okay, so this is the statistics behind the calculation of the accuracy of the instrument or the usefulness of the instrument. Now, can you think what should be done to improve this condition so that this probability will improve? Okay, so I want to have better instruments. So all the instruments are looking same. Say maybe there is a cost of instrument is 1,000 rupees in one case, and the same measurement you have another instrument maybe of say 10,000 rupees. Okay, they do measure the same thing, but what is difference between the two is this particular probability. Okay, so instrument is saying positive, then what is chance that you really have this case? So what doctor will do is it will take a rapid test or cheap test, and the doctor has to take a better test so that this observation is confirmed. Okay, so you cannot rely on one instrument. The doctors will ask you to go to somebody else and then have this better test. Okay, so this is a say 100 rupees test, and you have to have say 1000 rupees test. Okay, so that you will go with this instrument. So this is say the importance of base in this case. Okay, so that way if you look at the figures, 90% accuracy, 90% sensitivity, and 98% specificity, it looks very good instrument. Now to improve this situation, you have to improve the sensitivity of the instrument. So you may have say another instrument with 98% sensitivity and maybe 99% specificity, and then you can improve this calculation. So what I suggest you is you take this as a problem for homework. So you just change the figures to 98% from 90%, and just redo this calculation on your own and see what happens. Is this improving? Okay, then you can have part B of this problem. You will compute probability of condition being negative when test is negative. What will be this? Okay, so you will solve this at home, and then you take this as your data. So you take probability of the specificity as 99% and sensitivity as 98%. Or even you can try right now and type your answer in chat box. Now going back to the yesterday or day before yesterday's derivation. So we are discussing this decision boundaries for different situations, and we took the case. We took this case. This case number 1, where covariance matrix is same for sigma is same for all classes, and this sigma is of this nature. So this is a diagonal matrix, and all off diagonal elements are 0. And that too, sigma 1 1 square is equal to sigma 2 2 square is equal to sigma 3 3 square, and so on up to sigma dd square. Okay, so all these diagonal elements are having same value, and off diagonal elements are 0. So this was a typical case, simple case that we have seen in last class. So when I take these two conditions and proceed to find out the decision boundary between two classes, then I landed to this equation GIX, this one is equal to WI transpose X plus WI0, where WI is this thing and WI0 is this quantity. So this is threshold or bias, and this is the slope of the line, okay, or plane. Now decision boundary is determined by hyperplane setting GIX is equal to GJX. So you have GIX, so this is G1X, suppose I write here, then this will be W1 transpose X plus W1 0, and G2X is W2 transpose X plus W2 0. Okay, so this we obtain from this equation. Okay, I can put here I equal to 1, and then I can put I equal to 2. So you will get two different discriminant functions. So what is the use of this discriminant function? We have seen already. So this is X going to a box which implements G1X, and this is again going to a box which implements G2X. Okay, so they will produce their own outputs, and this is given to a max selector, and that will find out who is the winner in this situation, and index of that particular box will be your output. If say this is winner, then output is class 1. If this is winner, then output is class 2. Okay, so this is the situation. I'm just considering two class problem, two class multi-dimensional problem. So this X is a vector again of this form, d-dimensional. Okay, so this is going to this box, this is going to this box, and this function g1x will compute some value, g2x will compute some value. So whichever is closer, so this sample is closer to this function, then this will produce a largest value or the highest value compared to the second one. So I will say this belongs to class 1. If G2X produces larger value, then I will say this is G2X. Suppose I take a 1D case, then the situation is like this. Say these are two functions. Say this particular line is G1X, suppose, and this is say G2X. What happens is this x-axis is your input, and suppose your input is suppose here, say x test is lying here, then what happens is you put this thing in G1X, the output produced is this much. Okay, so this is your output for G1X, and what will be the contribution, sorry, G2X, what will be contribution for G1X? So you have to extend this plane or line, and then you will see that it will intersect here, and G1X will produce output here, G2X will produce output here. Okay, so in this case G2X is greater than G1X. Okay, So what happens is I will declare this text X test as belonging to class 2. Now suppose you have another input coming to you, that X test suppose dash, and which is lying here, then you will see that now G1X will have more value than G2X. So G2X will be this much. This is G2X negative side, and G1X is now positive. So in this case, G1X is winner. So this particular input belongs to class 1. Okay, this particular input belongs to class 2. So what is happening due to these two planes is that the space is now divided into two halves. From say this point onwards, this is class 1, and this point onwards is class 2. What if G1X is equal to G2X? What will happen? Where this will happen? So this is the point. If your input is here, in that case G1X is equal to G2X. So you really cannot find out to which side this input belongs. Then you say that this input is on the boundary. Okay, so if you find out in suppose a 2D case, you vary this X whatever way, and you search for a condition that G1X is equal to G2X, then you will face a situation where you will get intersection of two planes. Suppose like this is plane number 1, which is responsible for G1X, and you may have another plane, say passing maybe like this. Okay, you can imagine that, and maybe this is the intersection of two planes. I hope you can imagine. So this will be the line, and this will be G1X, and this will be G2X, and this line, which is the intersection of two planes, is the decision boundary. Okay, so same thing is written over here, that if I find out G1X is equal to G2X, that means the two functions are meeting each other. That will give me the equation for decision boundary. So the equation for decision boundary is this one: W transpose into X minus X0 equal to 0. So to obtain this, you have to take into account this equation. You have to take G1X and G2X. So if I write that way here itself, so this will be G1X is minus 1 by twice sigma square X transpose X minus 2 mu1 transpose X plus mu1 transpose mu1, okay, plus log of probability of omega 1. So this will be, you can note down this is equation number 1, and then you can have G2X again 1 minus 2 sigma square into X transpose X minus 2 mu2 transpose X plus mu2 transpose mu2 plus log of omega 2. Okay, so these are two equations. Now if I say equation number 1 is equal to equation number 2, that means G1X is equal to G2X. If I solve this now, if I solve this, say this is what this equation is saying, and then simplify that, you try this at home, you try to simplify that and try to bring that simplification in this form. Okay, so W transpose X minus X0, where W is given by this equation. So this will be mu1 minus say mu2, right? And X0 is given by this quantity. So this will be mu1, mu2, then mu1 minus mu2, like this. So this will be the intersection. This will be intersection or the constant part of your line or plane. And this will be the slope kind of thing. Now, if you see that equation, then it is passing through x0. It is orthogonal to the line linking the two means, that is mu1 and mu2. So this line, suppose this is mean of the class 1 and this is mean of class 2. So the line joining between these 2 points, then if you draw perpendicular to this, then this will be the decision boundary. So logically it seems good and correct that you are dividing the space into 2 halves. Okay, so that is what this derivation is telling you. So if you take say different cases, you change now priors. Say here prior is 0.7 and here prior for omega 2 is 0.3. So priors are different. So this line is moving towards the other, say omega 2. If prior omega 1 is equal to omega 2, what will happen is this decision boundary, instead of moving towards omega 2, it will be correctly passing through the center between these two classes. Okay, and this will be perpendicular. Now here in second situation, prior of omega 1 is 0.9 and prior of omega 2 is 0.1. So still this line is moving towards omega 2. So area of omega 1 is increasing since its prior is increasing, and area for class 2 is decreasing since its prior is less. So this will happen. Now if I take another case, say this one, you will see this plane is again shifting based on the priors. Okay, so these are different conditions given in Duda's book. You can refer to Duda hard book for more details. You can see this case. So this is a 3D case. This is a 3D case. This is a 2D case. This is a 1D case. In case of 1D, what happens is just we find threshold. There is no line. So this is dotted line is a threshold. You can see here. So this threshold onwards is omega 2 and threshold below is omega 1. Threshold onwards is omega 2 and threshold below is omega 1. And this line position is moving to right hand side since prior of omega 2 is less in this case compared to this. Okay, so this way we can study this classifier where this decision will be. Now when you take or when you design a classifier and you want to deploy this classifier for real life purpose, say you have designed a robot to classify a road and say mud. So you have some camera which is focused on the path of this robot, and then you have to classify the scene into 2 classes, that is road or mud. So if there is mud, you have to take some decision. If it is a road, then you have to take some other decision, and your decision wholly depends on what you see or the robot is seeing in front of it. In that case, suppose I want to implement this and I have extracted certain features. Suppose I have extracted only one feature then I need to just find out this X threshold for my problem. Okay, that kind of problem we have seen, taking into account the cost of taking a wrong decision. So if you classify mud as road, in that case it was costing us 1,000 rupees because it was destroying our robot. So that we have to take into account and decide this threshold. So once you decide this threshold, you have to remember only this much. Okay, so what you remember is, you remember this X threshold. Where it is some 2.5, let us say. So this 2.5 you have to remember. U means you have to write the program in your say microprocessor or microcontroller, and you have to remember this value, and whatever current value is coming to you, you compare with 2.5. If it is more than 2.5, say omega 2. If it is less than 2.5, say omega 1. Okay, that's all. So implementation is very simple, but to implement this, here we have to solve all this or do this calculation and then remember the thresholds. Now, if you have two features to solve your problem, so then you have to go for a 2D kind of thing. So this will be a 2D case. In case of 2D, see what happens is, the instead of threshold, there won't be any threshold now. There will be a line of decision like this. This you have to remember. And how you will remember? This is a simple line equation, y equal to mx plus c kind of thing. So you have to remember m, you have to remember c. Okay. Now when you go to more features, say you are going for 3 features to decide mud and road, situation will be like this. Okay. So instead of now decision line, you have a decision plane. So this side of the plane is omega 1, this side of the plane is now omega 2. Now what you have to remember? You have to remember now plane equation. So that means you will be remembering something like this. Okay, so you have to remember 4 variables and you have to solve this equation and then take a decision. If this quantity is greater than 0, you say omega say 1, or then you say omega 2. So this is the way we do it in real life. So we take a model, we solve for our given problem and find out the decision line or plane or threshold. So I am showing you 3 cases. This is 1D case, 2D case, 3D case. Suppose you extract 4 features for your problem. So what your robot is monitoring in front of the camera, and it is extracting 4 features for input. So like this, x1, x2, x3, x4. Then your problem becomes 4 dimension. Then you have to solve the equation for 2 classes, that is g1x is equal to g2x. Then this computation will result into hyperplane, which is of 4 dimensions. Okay, in that case you will have to solve w1x plus w2x and so on up to w5 equal to 0. So like that your complications will keep on increasing. So that time we will call this plane as hyperplane. More than say 3, we will say it is hyperplane. Okay, so now in next condition, case number 2, in case number 2, now this sigma I is same for all classes, but this sigma diagonal are different. So this sigma 1 1 square, sigma 2 square on the diagonal. Off diagonal elements are still 0, but this diagonal elements are not same. So sigma 1 square is not equal to sigma 2 square, not equal to sigma dd square. Earlier in case 1, this was also same. So we are now making more generalized thing, and again we will solve for g1x, g2x in same way, and we will try to find out w1, w2, and w10, w20. So if you simplify that, you will get these two things. So there will be modification in your x0. Okay, now x0 is modified, and I think even w is also modified if you compare with earlier things. Earlier thing was w is equal to mu1 minus mu2. Okay, and this was this x0. Now with some conditions made generalized, that is diagonal can take any value. This is what is generalization here. Then you will see that this sigma inverse is appearing here, and this sigma inverse is appearing here. Okay, if this was same, that is diagonal is elements are all same, then this will disappear. Okay, so if I compare with earlier case, but now this will exist, but still you will see that whatever I obtain is again line or plane. Okay, line or plane. And if you see closely, then the centroids of these two, if you join and if you take a line for this, then this may not be 90 degrees in this case. Okay, this need not be 90 degrees now. Earlier, in generalized case, if I join two mu's, then the boundary was exactly 90 degrees. Now, in this case, this may not be 90 degrees. That is what is happening due to the loosening of the condition that sigma 1 square is not equal to, say, sigma 2 square not equal to sigma dd square. So what is happening is the shape of your normal distribution is not exactly circle. So this is now elliptical. So if you say sigma 1 square is equal to sigma 2 square and take a 2D case, then you have a normal distribution with this kind of intersection. Okay, so they are like a circles. Now if I lose this condition that they may not be same, then the spread in this direction and spread along this direction is not same. That means it may be of elliptical shape. Okay, an intersection of that, so this is of this shape and this is of this shape, and then the decision boundary may be like this. Now here the decision boundary is like this, and this your mu1 mu2s are like this, so this will be 90 degrees. Now here mu1 mu2s are here, and the angle is not 90 degrees. Okay, so this kind of thing will happen. Now if I take more generalized case that every covariance matrix is different, that is for all classes they have their own sigma. In earlier two cases, this sigma was same for all classes, whatever may be diagonal, but it was same for all classes. Now the most generalized case is sigma is different for all classes. Then it will be most generalized case. And if you solve the previous way, then you have a quadratic form of your equation for g of x. So that will not be now line or plane, it will be a, you can say a shape which is non-linear. Okay, it will be a curvy nature. So if I see those cases, then you can see the decision boundaries are now becoming, see, elliptical or hyperbolical kind of things. So their decision boundaries are non-linear. The boundaries are non-linear. So we have seen three cases. Case one, where sigma is same for all, and all the elements, that is the diagonal elements, are same variance. Second case, sigma is same for all, but diagonal elements are different. Okay, that is variance can be different. Third case is sigma is different for all. Diagonal obviously can be anything. So this is the most generalized thing, and you will see that when you go to most generalized thing, the decision boundaries are becoming non-linear. That is what we want. We want that our system should handle non-linear decision boundaries. The real life situation is like that only. We cannot have only linear problems. We have to have non-linear problems. I will stop here. If you have any doubt, you can ask.